Hello everyone, and welcome to the lecture on aromatic substitution. So in the third edition of David Klein, this would be chapter 18, and in the second edition, it's chapter 17, I believe, or is it chapter 19? I can't remember anymore. Okay, here we go, aromatic substitution reactions. Okay, so first thing to remember is that aromatic rings, or their pi bonds specifically, are not as nucleophilic and reactive as isolated pi bonds, such as those from alkenes. So for example, if you treat an alkene with bromine, you get the anti-addition product. And if you treat benzene with bromine, nothing happens. So the pi bonds are much more stable due to the conjugated nature and the overlapping p orbitals in the ring, and because of the aromaticity essentially that we talked about in the last chapter. So they're much less reactive. However, if you treat benzene in the presence of bromine with a catalyst, such as iron or aluminum, then a reaction does occur. And instead of an addition reaction where we add two bromines to one of the pi bonds and get the anti-addition product, instead we end up with a substitution reaction occurring. So one of the hydrogens attached to the benzene ring is removed or substituted, and instead is placed a bromine on the ring. We call this an electrophilic aromatic substitution. And the term electrophilic actually comes from the reagent that's used, not the aromatic ring. So we are treating the aromatic ring with an electrophile, in this case bromine, or it's going to actually convert to a much more electrophilic species prior to reaction with the ring. And the ring itself actually acts as a nucleophile. So because we're treating the ring with an electrophile, we call it an electrophilic aromatic substitution. And that's important because later on we'll talk about nucleophilic aromatic substitution reactions. There are several electrophilic aromatic substitution reactions that are introduced in this chapter. We just looked at the introduction of a bromine. We can also introduce a chlorine in a similar reaction to introducing the bromine. We can introduce a nitro group, a sulfonyl group, an alkyl group, or an acyl group. There are other reactions as well, such as the introduction of an iodo group. That one is not covered in Klein's organic chemistry textbooks, but it will be covered in the lab course that is a prerequisite to this lecture course. So in all cases, the ring acts as a nucleophile and it's being treated with a strong electrophile. After the substitution reaction occurs, the aromaticity of the ring is preserved. That's one of the reasons why the reaction is favored, because we don't lose aromaticity overall in the reaction. We go from an aromatic reactant, such as benzene, to an aromatic product, such as the substituted benzene that we see here. So let's review the bromination of an alkene. Bromine does function as an electrophile in that reaction, and even though you see these little boxes, this is supposed to be delta positive, delta negative. If you recall from learning about the addition reaction of bromine with an alkene, we talked about the fact that Br2 is what we call polarizable. It's polarizable because these are large atoms and their valence electrons are held relatively far away from the nucleus. So the electron cloud can distort more than other atoms that are smaller. When they distort, especially that can happen if something electron rich approaches one side, then the electrons sort of distort to the other side of the bromine molecule, leaving the closer bromine delta positive or partially positively charged, and the other bromine with a partial negative charge. So the partial positively charged bromine is actually the electrophile, and the other bromine we would call a leaving group. In order to make Br2 even more electrophilic than it normally is, we need to treat it with a Lewis acid. So in this case, Br2 is not electrophilic enough to react with benzene. But if we treat it with a Lewis acid catalyst, such as iron, and again, I said aluminum would also work well for this, it will actually react with some of the bromine, or if you were using, doing a chlorination, it could be Cl2, and it would produce iron 3 bromide or chloride. And this is actually the Lewis acid catalyst that reacts with another molecule of bromine to produce the active electrophile that we'll see on the next slide. So once the Lewis acid catalyst iron 3 bromide has been prepared, it actually acts as a Lewis acid, and bromine here is acting as the Lewis base. So this is a Lewis acid base reaction, where a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. So this is different from a Bronsted acid base reaction, which involves a proton transfer, but instead just involves a electron pair acceptor and an electron pair donor. So when that reaction occurs, you get a complex. So the intermediate here we call the Lewis acid base complex. And you can see that the iron, by receiving those extra electrons, has taken on a negative charge, and the bromine has a positive charge. So this bromine is now electron deficient, and it's possible for the bromine-bromine sigma bond to break or cleave heterolytically to give the lone pair, or the electrons in the bond, to form a lone pair on the bromine. That leaves Br with only 6 electrons, a full positive charge, and a very, very potent electrophile. So this reaction mechanism can be a little bit confusing because depending on the source, they may just use Br plus as the active electrophile, or they may use the complex directly as the active electrophile and have the nucleophile attack this terminal bromine and have this leaving group leave at the same time. So sometimes a nucleophile comes in and attacks this bromine to have a leaving group, loss of a leaving group. Iron with 4 bromides attached is the leaving group. And other times they'll just show this bond breaking prior to the nucleophilic attack. So basically loss of a leaving group occurring prior to nucleophilic attack and then having the nucleophile attack here. So it's just your preference of whether or not you believe that Br plus is forming in solution or you don't, and different organic chemists will disagree on this. Okay, so instead of using Br plus, notice the active electrophile used in this mechanism is the complex, and that's okay. You could have the aromatic ring pi bond functioning as a nucleophile to attack Br plus or to attack the bromine in the complex with simultaneous loss of a leaving group. Either way, you get the same intermediate. So it doesn't really matter how you draw that first step. The intermediate has a name. It's sometimes called the sigma complex and sometimes called the irenium ion. So I wrote the name here, irenium ion, down here. So you can see when I'm referring to the sigma complex or the irenium ion, I use those terms interchangeably. And they basically mean the intermediate formed in an electrophilic aromatic substitution, which is a resonance stabilized intermediate. You can see the 3 contributors here for this particular reaction. And after that intermediate forms, we get loss of a proton, so it's a proton transfer to re-aromatize the ring. And because there's no water or other good base around, oftentimes they will just start from the iron-bromine bond to do the proton transfer, or they'll just use bromide as the base to pick up this proton and re-aromatize the ring. So notice I mentioned that the second step re-aromatizes the ring. So that means the intermediate is not aromatic, and that is true. If you look at this carbon here, it has 4 atoms attached. So it is sp3 It does not have a p orbital, and therefore this ring cannot be aromatic. So the intermediate is higher in energy than both the reactant and the product because it's non-aromatic, whereas the starting material and product are aromatic. Notice the energy diagram, right? We talked about the sigma complex. Even though it's resonance stabilized, it's still much higher in energy than the reactant and the product. And the reactant is benzene. They didn't show it here, but it's benzene. It's much higher in energy because, again, the sigma complex / rhenium ion is not aromatic, and the reactant and product are. The reason why substitution is preferred is because of the stability of the substitution product. Because it's aromatic, it's much more stable, low energy, and it will be favored. We mentioned that there are other catalysts that could be used in the bromination besides iron or aluminum. You could also just add aluminum 3-bromide or iron 3-bromide. So basically over the arrow you might see just iron by itself, just aluminum by itself, or FeBr3 or AlBr3. Because if you just add iron or aluminum, those will react with bromine to form iron 3-bromide or aluminum 3-bromide. So you can just add the iron 3-bromide or aluminum 3-bromide instead of allowing for the reaction to occur between these two. Either way, it ends up forming one of these Lewis acid catalysts that catalyze the reaction. We can also do the same thing with, instead of Br2, Cl2. Right? We would just want to use, of course, the matched Lewis acid catalyst with the correct halogens so as not to get any strange halogen exchange or to prevent the formation of more than one product. In general, fluorination with F2 is too violent to be practical. It's difficult to control that reaction, and iodine is generally too slow with low yields. In the lab course, as I mentioned, there will be an alternate set of reagents to introduce an iodine to a ring. So let's look at the mechanism for the chlorination of benzene. It's basically the same as the bromination of benzene, where instead of bromine having reacted with the Lewis acid catalyst, chlorine reacts, right? And so we form this very analogous active electrophile, which the poor nucleophile is able to attack because it's such a strong electrophile. Again, the same sigma complex / rhenium ion is formed, and the second step is proton transfer to re-aromatize the ring. In general, we're going to be looking at a variety of different electrophilic aromatic substitution reactions, and they're all going to follow the same two-step mechanism, where the benzene ring, or aromatic ring, attacks the active electrophile, whatever that may be, and this varies depending on what's getting added to the ring. We form the resonance stabilized rhenium ion / sigma complex intermediate, and a proton transfer occurs where a base takes the proton on the same carbon that the electrophile was attached to the electrons from the carbon-hydrogen bond flow over to form a carbon-carbon double bond to re-aromatize the ring. So the base also varies depending on the exact EAS reaction and exactly what electrophile is being added and exactly what the reaction conditions are. The next EAS reaction we're going to learn is sulfonation. That's the introduction of what we would call a sulfonyl group. Okay, this is really only an important group for organic chemists because this reaction is reversible. And we're going to talk about how the addition and removal of this sulfonyl group has a very interesting and important synthetic advantage in doing some organic synthesis. So we're going to get back to that. But the conditions to introduce the sulfonyl group are concentrated or fuming sulfuric acid. So concentrated sulfuric acid solution is like a 12 molar solution, so very concentrated acid solution. And it's so concentrated that when you open the bottle, you can see fumes essentially coming right out of the bottle. Those fumes are SO3 gas, so the sulfur trioxide gas, and it is the active electrophile in the reaction. Okay, so sulfuric acid is actually just the acid catalyst. The actual electrophile is what's in the fumes, right, which is SO3. If we look at the structure of SO3, you can see it drawn down here. The sulfur atom is highly, highly electrophilic. It's bonded to 3 oxygen atoms. So oxygen is more electronegative than sulfur. So it's going to be pulling electron density from the sigma bond towards it, leaving the sulfur with a partial positive charge. But in addition, even the pi electrons spend more time around the oxygen than the sulfur. And while we might see these drawn as double bonds, they actually have quite a bit of single bond character because of insufficient p orbital overlap. The reason why there's inefficient p orbital overlap, which is essentially the formation of the pi bond, is because of the size of the p orbital being used to form the pi bond. Oxygen is using a 2p orbital, atomic orbital, and sulfur is using a 3p. So because they're not the same size, they actually don't have as much of an overlapped region, and therefore the pi bond is not as strong as it would be, for example, if the sulfur was a carbon. A carbon would use the same size p orbital as oxygen because they're in the same row of the periodic table, and it would form a much stronger pi bond than a sulfur trying to form a pi bond with an oxygen. So because of inefficient overlap of these 2 p orbitals, the pi bond is weak. There's a significant amount of single bond character between the sulfur and the oxygen, with a lot of the electrons from both the sigma and the pi bond between sulfur and oxygen residing around the oxygen. So that shows you with the electrostatic potential map why it's so blue, right, or so electron deficient at the sulfur atom, because primarily the electrons from both the sigma and the pi bond are around oxygen. So sulfur itself is highly electrophilic, which makes it a great electrophile to react with an aromatic compound. Because remember, the pi bond in an aromatic ring is a very poor nucleophile. So when that happens, and it's a poor nucleophile because it's stable. So when that happens, you need to react it with something very, very electrophilic to get a fast reaction. So the mechanism of the EAS reaction, specifically the sulfonation, involves the pi bond of the aromatic ring doing a nucleophilic attack on the sulfur of SO3, and we can draw one resonance arrow to move electrons up to the oxygen. That gives us the intermediate that we call the sigma complex or the rhenium ion. Again, it's resonance stabilized, and you can see those resonance structures drawn out with the allylic positive charge resonance pattern. Water is there in this case because remember we added a 12 molar sulfuric acid solution, so there's definitely some water around. So we can use water as the base to do the proton transfer to re-aromatize the ring. And then finally at the end, a sulfuric acid, which has formed hydronium ion, can transfer a proton to make the sulfonyl group neutral and more easily isolatable for an organic chemist. As I mentioned before, the sulfonation reaction is reversible. If we use a very concentrated fuming sulfuric acid solution, it favors introduction of the sulfonyl group, or it favors the forward direction. And if we use a dilute water solution, it actually favors the reverse direction. So that is, we are able in this way to add and remove it. So we can think of it as a blocking group or a protecting group for this hydrogen. And again, the implications and the importance of that will come more into play when we start talking about synthesis later in the chapter. The next EAS reaction is the nitration, and the reagents are nitric acid and sulfuric acid. Nitric acid forms the active electrophile, which is called the nitronium ion, and the sulfuric acid is just an acid catalyst. Sulfuric acid is a stronger acid than nitric acid, so it's one of the few acids that's actually strong enough to be able to protonate nitric acid. And again, the active electrophile is believed to be the nitronium ion. So how is that nitronium ion formed from nitric acid and sulfuric acid? We talked about how sulfuric acid is a stronger acid, so we can actually do a proton transfer where nitric acid acts as a base to take a proton from sulfuric acid. You might have thought of using the oxygen with the negative charge to pick up the proton from sulfuric acid, but we're not going to do that. And the reason why is that the oxygen is actually stabilizing the positively charged nitrogen. So when you have atoms where there's a formal positive charge next to a formal negative charge, this is called a zwitterion. So this is actually a zwitterion and it's fairly stable, so those opposite charges are stabilizing one another. So actually the OH group is the more basic, which is not entirely intuitive when you just look at the structure. So it can pick up a proton, and then you can think of this as a good leaving group. Once it's a good leaving group, it can leave. We can draw this resonance arrow to kick it out, and we've lost water and we've formed the nitronium ion. The nitrogen atom of the nitronium ion is highly electrophilic. Again, a great active electrophile to react with a poor nucleophile in an aromatic ring. So here's our active electrophile. It is being attacked by the pi bond in an aromatic ring, such as benzene. This is a resonance arrow, right? So that we avoid exceeding the octet around nitrogen in this step. We formed the sigma complex / arenium ion. Water is present in this reaction to act as a base to reform the aromatic ring. Something important to know about the nitro group is that it can be reduced to an NH2 group. Because the nitrogen is directly attached to an aromatic ring, we don't actually call it an amine, we call it an aniline. An aniline is basically a amine where the nitrogen is directly attached to an aromatic ring. So if we use iron metal or zinc metal with an acid catalyst, we can reduce the nitro group. The initial product would be the protonated amine, or what's called the ammonium ion. So the second step is actually a basic workup in order to deprotonate the ammonium ion to reform the neutral amine, which is more easily isolated for an organic chemist. So combining these three reactions, we have a way to make aniline from benzene. We can do an nitration, which is a type of electrophilic aromatic substitution reaction. We can do a reduction with iron or zinc metal, and with a basic workup, we'll be able to isolate the neutral aniline. The next EAS reaction we're going to talk about is alkylation. And this one actually, it has a named reaction. We call it the Friedel-Crafts alkylation reaction. And it reacts, or the reactants, excuse me, are an aromatic ring, of course, and an alkyl halide. So the alkyl halide actually forms the active electrophile in the reaction, and it does so by reacting with a Lewis acid catalyst such as aluminum chloride. Notice the alkyl group gets introduced or substituted for a hydrogen on the ring, and we're able to introduce an alkyl group. So how does this reaction work? Let's start with the alkyl halide. It will act as a Lewis base to react with our aluminum trichloride, which is a Lewis acid. We say then it forms the Lewis acid base complex, and then this positively charged chlorine, which is electronegative, can start to pull these electrons away from the carbon. And if it does a full formal loss of a leaving group, the leaving group is AlCl4, and the other product of this step is a carbocation. Always remember with carbocations, we form tertiary carbocations or resonance stabilized carbocations very easily and quickly. Secondary carbocations are okay, But whenever you form a secondary carbocation, always consider rearrangement, because if it can do a hydride shift or a methide shift, it will do so to get to become more stable. And we never, ever, ever draw primary carbocations. So that's something to remember when you're drawing a mechanism. Never draw a primary carbocation. This is okay because it's a secondary carbocation, right? But we're not going to draw primary carbocations. That's important. They're too unstable to form. So this secondary carbocation is the active electrophile. The pi bond in the aromatic ring is acting as the nucleophile, doing a nucleophilic attack. We get the intermediate sigma complex / rhenium ion, and chloride, right, which you can also draw the proton transfer starting from the chlorine aluminum bond, will actually come in and act as the base, take the proton to form a pi bond and regenerate the aromatic ring. So with simple primary alkyl halides, this slide is a little misleading. I should have changed it. It says simple primary alkyl halides can be used effectively. That's true, but only this simple primary alkyl halide, which is ethyl chloride or ethyl bromide would also work, okay? Not anything longer. So for example, if this alkyl chain was a propyl or a butyl, this reaction would not work the way it's working here. So we're able to introduce an ethyl group, but we're not able to introduce a propyl group or a butyl group. And again, we're going to talk about why that is in just a minute. By the way, we could also introduce a methyl group. So instead of ethyl chloride, if I had had methyl chloride, for example, I would have introduced a methyl group here, and that reaction works just fine with, again, with the Lewis acid catalyst. So because simple primary carbocations cannot form, right, the electrophile is presumed to be the complex that's formed between the alkyl halide acting as a Lewis base, reacting with the Lewis acid, which is the aluminum trichloride. Once it forms the Lewis acid base complex, the carbon attached to the very electrophilic chlorine is the carbon that's the active electrophile in the reaction, because essentially it's the alpha carbon attached to the leaving group. So it makes sense that nucleophiles will attack that carbon specifically. Okay, so it did not show the entire mechanism, but basically instead of forming a carbocation, which we don't form primary carbocations, so it is not appropriate for you to show loss of a leaving group at this point. Instead of that, this entire complex is the active electrophile, and the aromatic ring's pi bond will attack this carbon and essentially do an SN2 reaction to kick out this giant leaving group. So that is the way the reaction proceeds in this case. Let's look at a alkyl group that's longer than 2 carbons. So I mentioned like a propyl group or a butyl group. This example is a butyl group, right? So butyl chloride. Once it reacts with the Lewis acid catalyst, it forms the Lewis acid base complex. At this point, something can happen that does not happen if this is an ethyl group. Specifically, we can get a hydride shift and simultaneous loss of a leaving group to form a secondary carbocation. If this had been an ethyl group, right, this carbon would be a methyl. A hydride would not occur because you would be again forming a primary carbocation, which we don't form. But because this is a longer alkyl group, right, when we do a hydride shift from this beta carbon, we end up with a secondary carbocation, which is stable enough to form. So this can happen, leading essentially to a mixture of products, because the Lewis acid base complex can act as the active electrophile in the reaction, and that can lead to the first product that you see here. Or we can have loss of a leaving group with a simultaneous hydride shift to form a secondary carbocation, which can act as the active electrophile in the reaction with benzene or any other aromatic compound. So that can lead to the second product, right, which is a bit of a problem. Organic chemists never like reactions that form mixtures because these would be very difficult to separate. Imagine they have similar polarity, they're going to have a similar boiling point, right? So all of our methods of separation are going to be useless to try to separate these two compounds. So this is not a very good reaction. So essentially they gave a mixture of rearranged and not rearranged products. So this is not an ideal reaction. So essentially what I want you to remember about the Friedel-Crafts alkylation reaction is what sort of alkyl halides are okay. It's okay if it's tertiary or secondary. It's okay if it's primary as long as it's no longer than an ethyl group attached. And then also methyl is okay, right? So you can use methyl chloride, ethyl chloride, or any secondary or tertiary alkyl halide would be okay. But propyl chloride and butyl chloride and anything longer chain where this is a primary carbon is not good because of rearrangement. So let's do a practice problem so we can also show how we can draw products from this reaction. I will let you guys pause the video at this point. You can think about predicting the products of this reaction. You can think about whether or not you might get more than one product, or if you think you're only going to get one product, okay? And the mechanism to explain those products, the mechanism to explain their formation. All right, so let's go over this, right? We are, again, going to be predicting the products and drawing a mechanism. So recall that we don't have the active electrophile yet in a Friedel-Crafts alkylation reaction. What we have is an alkyl halide and a Lewis acid catalyst, and those must react together before you can form the active electrophile. So I'm just going to turn this around just for convenience. Remember, when I'm drawing in a mechanism, I always include important lone pairs. I'm going to draw out the Lewis acid catalyst. Can add in all the lone pairs on the chlorines. And the first step is that Lewis acid base reaction, right? So the alkyl halide's lone pair on its chlorine will act as a Lewis base and form a bond with the aluminum, which is electron deficient. So that's going to form the Lewis acid base complex. And at any point, if you get tired of drawing out this aromatic ring, you could just use an abbreviation like pH or phenol or something, okay? So we have the formation of the complex. Don't forget to draw in all the lone pairs and the formal positive and negative charge. So the formal negative charge is on the aluminum, the formal positive charge is on the chlorine. So at this point, because the chlorine is attached to a secondary carbon here, we can have loss of a leaving group. Remember, we would not do this if we were forming a primary carbocation. So because we're forming a secondary carbocation, it is reasonable to show loss of a leaving group. That gives us a secondary carbocation and the leaving group that is left, AlCl4. So at this point, whenever you form a secondary carbocation, you usually want to look to see if there's any rearrangement is possible. And it is possible, right? Particularly because if we do a hydride shift, we're going to get a more stable carbocation, not because it's more substituted, it'll still be secondary, but it'll be secondary benzylic which is much more stable than secondary. So I'm showing a hydride shift. And that gets me to a secondary benzylic carbocation. So here's the problem with reactions where rearrangements occur. This doesn't occur 100% of the time, right? So sometimes the benzene will attack this carbocation before rearrangement, and sometimes the rearrangement will occur prior to the nucleophilic attack. So there's really two active electrophiles in solution, right? So we have two different active electrophiles, and they're different and they're going to form different products. Right? So either one of those can be attacked by the benzene ring, right? Just benzene, which is our reactant over here. So we can show if the aromatic ring, right, was to attack the first one, then we would get you can think of essentially this one or possibly the other carbocation. Right? Either of those, we could do the nucleophilic attack. This is going to lead to a mixture of products. The intermediate is the rhenium ion. At this point, I'm just going to abbreviate this as phenyl just to save space. Okay, so hopefully everybody understands that this is the quote, the phenyl. Okay, so it has a purple group attached. The nucleophile is the pi bond that attacks directly on this carbon, right? Because that's where the positive charge was. And that leaves this resonance stabilized sigma complex / rhenium ion. I could draw out the resonance contributors of these, but I don't have to unless I'm asked to do so. Right? If I had the product from this particular pathway, looks very similar. Right, but we're attacking a different carbon, right? So we end up with a slightly different alkyl attachment here. Either way, it forms its own rhenium ion, and the base, which is either going to be chloride, or you could draw this entire thing out to use the aluminum chlorine bond, but essentially you can just use chloride, right? And it will do proton transfer to regenerate the ring. We can show the same thing over here. Proton transfer to regenerate the ring. And that's going to lead to our products. This is the last step. We form some HCl and the product. So the products are two different products, right? We have essentially added in and formed this compound, and now I've redrawn the phenyl out as opposed to leaving it abbreviated. And we also formed some of this product as well. Now you might ask me which one is major and which one is minor. So the answer to that is, I think I might have, oh no, I did screen share this. The answer to that is usually the rearranged product is the major, right? So this one is the one that, the purple one is the one that rearranged. So we're going to label this as major, right? And this is minor. Okay. So there are some limitations that you want to be aware of regarding the Friedel-Crafts alkylation reaction. And that is that because we are either forming a carbocation or attacking the complex, which will involve an SN2 reaction, either way, we're essentially doing an SN1 or an SN2 reaction. So the carbon attached to the halogen cannot be sp2. Right? It has to be an sp3 hybridized carbon because we again are either forming a carbocation and essentially doing an SN1 reaction, or we're doing an SN2 reaction on the complex. Either way, the alpha carbon must be sp3. So both of these reactions would not work because the alpha carbon is sp2. With Friedel-Crafts alkylation, polyalkylation is a bit of a problem. And the reason that this happens, the reaction happens more than once, is because the product, after it's added a single alkyl group, is actually more nucleophilic than benzene. So tert-butylbenzene is more nucleophilic than benzene. And that's because the alkyl group is a weak electron donating group. But regardless, even though it's weak, it's still an electron donating group. And it's donating electrons into the aromatic ring, making it more electron rich and more nucleophilic. So the product is actually a better reactant for electrophilic aromatic substitution, and specifically Friedel-Crafts reaction in this case, than benzene is itself. So oftentimes, because the product becomes increasingly more nucleophilic, the aromatic ring just keeps substituting repeatedly. Another substitution, and this one is really important, is that you cannot do a Friedel-Crafts alkylation reaction or the next Friedel-Crafts reaction that we haven't talked about yet, the acylation reaction. You cannot do that with a strong electron withdrawing group attached to the aromatic ring. So nitrobenzene, the nitro group is a powerful electron withdrawing group. It's actually pulling electron density out of the ring, making this even more complex, than it already is. So benzene is a poor nucleophile. Nitrobenzene is a really poor nucleophile because the nitro group is withdrawing electron density out of the ring. And it's even less electron rich than it was before. So when you have a powerfully or moderately deactivated ring, and you'll understand what I mean by those terms shortly. Unfortunately, we cannot do Friedel-Crafts reactions. And that's because Friedel-Crafts reactions, while they use powerful electrophiles like carbocations, for example, the electrophile is not powerful enough to overcome the poor nucleophilicity of this particular ring. So that's something to be aware of. No Friedel-Crafts reactions on a aromatic ring that has either a strong or moderate electron withdrawing group attached to it, or basically if it's moderately or strongly deactivated overall, because there can be multiple substituents, which we haven't talked about yet. Some of them can be donating, the others can be withdrawing, but if overall there's a moderately or strongly deactivated ring, it will not do a Friedel-Crafts reaction. So that's something to be aware of and will become important synthetically later on. The second Friedel-Crafts reaction is the Friedel-Crafts acylation reaction. So instead of introducing an alkyl group, we introduce an acyl group. You can see the difference here drawn in red. And the reaction is very similar to an alkylation reaction, but instead of using an alkyl halide, we're using an acyl halide, which essentially the alpha carbon is a carbonyl. We still use our Lewis acid catalyst, we generate a different active electrophile, and it will react with an aromatic ring, again, as long as it isn't powerfully or moderately deactivated overall, and it will introduce an acyl group. Let's look at how we can generate the active electrophile known as the acylium ion. The acyl halide, the chlorine specifically, one of its lone pairs can act as a Lewis base, attack the Lewis acid, again forming that Lewis acid-base complex. Loss of a leaving group can occur to form what's known as an acylium ion. That acylium ion is resonance stabilized, and the positive charge is shared between the carbon and its neighboring oxygen. Let's look at that resonance stabilization. These are the two resonance contributors that we can draw by the partial sharing of one of oxygen's lone pairs to the electron deficient carbon. Either way, the carbon is highly electron deficient and a great electrophilic atom for an electrophilic aromatic substitution reaction. So you can draw either resonance contributor of the acylium ion, that is the active electrophile for the aromatic ring to attack. And then again, in these Friedel-Crafts reactions, no water is present, so we use chloride as the base to regenerate the aromatic ring in the product. Okay, remember we talked about we unfortunately cannot introduce a propyl or a butyl group through Friedel-Crafts alkylation because of rearrangements. So if we want to introduce a propyl group or a butyl group, we actually need to do a two-step process. This will avoid rearrangements and you'll only get a single product, which is very advantageous for organic chemists. So instead of doing a Friedel-Crafts alkylation with butyl chloride, which will lead to a mixture of products, we can do a Friedel-Crafts acylation with a 4-carbon chain alkyl halide, or acyl halide, excuse me. It will do a Friedel-Crafts acylation, and then we're able to reduce this carbonyl after the reaction using what's called a zinc-mercury amalgam, which is basically like an alloy of these two. Under acidic conditions with heating, we will be able to reduce benzylic carbonyls all the way down to the alkyl or CH2 group here. This second step is called a Clemmensen reduction. So when you use a zinc-mercury amalgam, you can reduce a benzylic carbonyl. It's called the Clemmensen reduction, and it reduces down to a CH2 group. By the way, the Clemmensen reduction will also reduce a nitro group. If you remember previously, we talked about reduction of a nitro group to aniline in the presence of either zinc metal or iron metal with HCl, right? So if we use a zinc mercury amalgam instead of zinc metal, it still has zinc metal in it, and it will still reduce a nitro group to an NH2 group. And it will also reduce benzylic carbonyls. So that's something to be aware of, that this can do double duty depending on the substrate. If there's both a nitro group and a carbonyl, it would reduce both of those. Unlike alkylation, Friedel-Crafts alkylation, polyacylation is not observed. Okay, so polyalkylation is a problem, but polyacylation is not a problem. And the reason is the product, which contains one acyl group attached to the benzene ring, is actually moderately deactivated. So the group that's been attached here is a moderate electron withdrawing group. Remember, I talked about you cannot do Friedel-Crafts alkylation or acylation on a moderately or strongly deactivated ring. So this ring is moderately deactivated by this moderate electron withdrawing group. So it will not do a Friedel-Crafts reaction, and you won't get a second addition of an acyl group. So that actually can be an advantage, because usually you don't want to do a polyacylation or alkylation. So it will prevent that from happening twice, which is a good thing. Okay, let's do a practice problem I would like you to think about how you would synthesize this compound from benzene. Remember, we're in the Friedel-Crafts acylation section. So you might want to think about how to use a Friedel-Crafts acylation reaction to make this product. So go ahead and pause the video and think about how to do that. Okay, so let's think about how we would do that. So we're starting from benzene, right? And we're thinking about possibly using multiple steps to get to the product here. So we talked about using a Friedel-Crafts acylation reaction. So if we're using an acyl halide, perhaps we would want to just introduce the carbons that we need attached here. So you can use any acyl halide that you want and a catalyst. Okay. And then that would give us the acylated product. Which we then can convert to the product through a Clemmensen reduction. So again, we're using that zinc mercury amalgam, HCl, and heat to do the Clemmensen reduction. Again, this is another great application of the Friedel-Crafts acylation followed by Clemmensen reduction in order to introduce an alkyl group to an aromatic ring. You might have thought of, well, why don't I just do a Friedel-Crafts alkylation? Right? I can easily just replace this with a chlorine and use an alkyl chloride, and I can get that product. But the problem is that if you use an alkyl chloride, right? So just so I'm really, really clear, right? Let's look at an alternate, not good option of using an alkyl chloride. You might think, well, I can just use this alkyl chloride and get the product, right? But the problem is this is a primary carbon. You always have to worry about rearrangements when you're using a primary alkyl halide. This will easily rearrange to a tertiary carbocation, and you will not get very much of this product, if any at all. You would probably get a significant amount of the rearranged product, right? So I put a big X because this doesn't work, right? You would most likely get a significant amount of a totally different product that you were presumably not aiming for, which would be the rearranged product, which looks like this one. So this would be the major product from the Friedel-Crafts acylation reaction. So we don't want to do that. Instead, it's much better to do an acylation followed by a reduction than an alkylation. Okay, going back to our slides, we are going to start talking about the reaction, so electrophilic aromatic substitution reactions, where we're not using benzene anymore as the starting material. Instead, we're using substituted aromatic rings, right? So they have one or more groups already attached to the ring. So for example, when we do a nitration, which is an EAS reaction, on toluene instead of benzene, we actually want to think about two things. First, we want to consider how will the methyl group affect the rate of nitration, right? So will this reaction occur faster because of the presence of the methyl group compared to benzene, which would only have a hydrogen there? Or will it occur slower, right? So how does this affect the rate of the reaction? Because if the rate becomes too slow, the reaction won't occur. So that's the first thing to consider. Well, as it turns out, if you do rate studies where you're using similar conditions, or the exact same conditions. The only difference is benzene versus toluene. Toluene reacts much faster than benzene in this reaction. So the methyl group then is considered to be an electron donating group and what we call an activating group. So we say it activates the aromatic ring to act as a nucleophile in an electrophilic aromatic substitution reaction. So that is actually a good thing. The second thing to consider is the regioselectivity of the reaction. Where does the nitro group go, right? There's actually 3 different products where we introduce a nitro group at 3 different positions on the ring. The nitro group could go ortho, meta, or para. These are the products drawn out where the nitro group has been added ortho, meta, and para. And you can see the product distributions in bold on the bottom. So the ortho product is the major product, but we also have a very significant amount of para-nitrotoluene being formed and only a very small amount of meta-nitrotoluene being formed. So what we say, the ortho and para products predominate, right? And we don't have very much meta product. So then that becomes the fact that we talk about the methyl group is then an ortho-para director, because the presence of the methyl group is, quote, directing the nitro group into the ortho or para position. So it becomes what's called an ortho-para director. Why do the products favor ortho and para and not meta? Well, if we look at the intermediate rhenium ion, we can see that with the rhenium ion or sigma complex that forms in each case with ortho, meta, and para attack, we get a resonance stabilized rhenium ion in all 3 cases. However, these ones that are highlighted in green are particularly stable and for that reason particularly significant resonance contributors. Notice where the carbocation is in these structures. It's on a tertiary carbon. If you look at the meta attack, the carbocation ends up in all 3 cases on secondary carbons. Here it's secondary, secondary, tertiary, secondary, secondary, tertiary, and the meta attack is secondary, secondary, secondary. So the intermediate is much more stable from ortho and para attack. If the intermediate is more stable, those intermediates form faster, right? And we're likely to get those as the major product. You can think of the activation energy for the rate determining step in this reaction, which is the first step. It's much higher for the formation of a less stable rhenium ion. So ortho and para attack are actually a little favored compared to meta attack. So then why did we get more ortho than para, right? They look kind of similar. The reason in this particular case is because it's basically probability. There's 2 ortho positions and there's only 1 para position, right? So depending on how the reactants react, it's just more probable to get more ortho product. So this I actually think is not a very good example that Klein is using here. And let me explain the reason why I don't particularly like this example. The reason why is when you have an ortho-para director, in pretty much all cases except for this one, the para product will be the major product. So this really makes students think, oh, the ortho product can be the major product. But in reality, it only can be the major product in this reaction. In all other cases, almost exclusively, you can pretty much just say the para product is the major product. So I just talked about why the ortho product is major because there's 2 ortho positions, right? But the para product has a significant advantage as well in that there's less steric hindrance. The nitro group and methyl group get kind of close together over here with ortho, but they're much further apart in the para product. So the para product can be much more stable than ortho when there's steric hindrance to worry about. The reason why there isn't that much steric hindrance in this particular example is the nitro group is fairly small and the methyl group is small, right? But if this was to get any bigger, like ethyl, all of a sudden the amount of this goes down drastically and the amount of the para product goes up a lot, right? So I want you guys to basically just think of, except for this very one reaction, when you have an ortho-para director, it directs para first, and only ortho if the para position is blocked. That's really, really important. So ortho-para directors direct para first, and only ortho if the para position is blocked. And again, that's because a lot of the other electrophiles are larger groups, so there's more steric hindrance to worry about, so the para product is actually a lot more stable. And also the directing group can be much larger as well in other cases, and that can also help destabilize the ortho product. Okay, in this slide, you can read it, but basically it talks about how this is an exception, exactly what I was just talking about, and how we're going to use it as a general rule that ortho-para directors direct para first. Okay, what about the methoxy group, right? Here you can see a methoxy group. So this is, if you remember your aromatic nomenclature, right? This is anisole. Anisole has an aromatic ring with a methoxy group attached. So the question is this an electron donating group or an electron withdrawing group? And actually, it is an electron donating group, and anisole it reacts 400 times faster than benzene. So it's overwhelmingly donating electron density into the aromatic ring compared to withdrawing it. It's a little bit confusing though, because you're taught oxygen is electronegative. Through induction, it's actually going to be pulling electron density towards it and out of the ring. And that's true. The methoxy group is electron withdrawing through induction. That is still true. However, it is electron donating through resonance. So while it's withdrawing electrons through its sigma bond, right, it is donating electrons through the overlapping p orbitals known as the pi bond. So it is actually donating electron density into the ring, and you can draw all these resonance contributors which have a partial negative charge inside the ring. Notice specifically that partial negative charge is at the ortho and the para positions of the ring. So again, that's another reason why the methoxy group is an ortho-para director. Look at where those partial negative charges are on the structure. Those are the carbons that are particularly electron rich, and we know in an electrophilic aromatic substitution reaction, the aromatic compound is acting as a nucleophile. So the electron rich positions are particularly reactive. It's so reactive that it will actually react with bromine to do an electrophilic bromination, and it will introduce the bromines without a catalyst. So notice how you don't even need an aluminum or iron catalyst for this, and it will introduce 3 bromines very quickly in the ortho and para positions. So it is so activated, we don't even need a Lewis acid catalyst to make the bromine more electrophilic. Bromine, even without the catalyst, is electrophilic enough to react with this very nucleophilic aromatic ring. Okay, so remember, all activators are ortho-para directors. That's extremely important. Okay, so the methoxy group is an activating group because it makes the ring react faster than benzene. So it's just a rate comparison. And it's also an ortho-para director. So the methyl group and the methoxy group are both activating, although the methoxy group is much more activating than the methyl group, because the methoxy group donates electron density through resonance, and the methyl group only donates electron density through induction. But because they're both activating groups, they're both ortho-para directors. So let's look at the nitration of anisole. Where is the nitro group going to go? Now it prefers the major product is para-nitroanisole. Right, so notice how this methyl group got a little bit more bulky. Now it's a methoxy group, and the para product is now the major product over the ortho product because of steric hindrance. We look at the stability of the rhenium ion / sigma complex formed from ortho, meta, and para attack. We see that the rhenium ion is actually much more stable from ortho and para attack compared to meta attack, because now there's a fourth resonance contributor where the positive charge is no longer just delocalized at 3 positions in the ring, but also on the oxygen atom. So now it's even more stable, and it is a very strong ortho-para director. Again, it's going to have a much lower activation energy to get to a much more stable rhenium ion. So the meta attack is very unfavored. The nitro group is an example of a deactivating group. It inductively withdraws electrons, and it also withdraws electrons via resonance. So you can see all the resonance contributors, they actually have a positive charge in the ring. So that's making the ring even more electron deficient than it would be if it was just benzene. So it is actually an example of a strong electron withdrawing group and a strong deactivating group. Even though it's a deactivating group, the ring can still react. It cannot do a Friedel-Crafts reaction. Remember, we cannot do a Friedel-Crafts reaction with nitrobenzene, but it can do the other electrophilic aromatic substitution reactions, and it can even add another nitro group. And look at the major product here, the meta product, right? So the meta is the major product. So the nitro group is a deactivator, strong deactivator, and it's a meta director, right? You can see the product distribution there. Let's explain why it's a meta director. It's a meta director because ortho and para attack lead to particularly destabilized rhenium ions with a positive charge right next to the powerful electron withdrawing group. So this destabilizes the intermediate, and as a result, meta attack is the best of the worst. It's the not very stable rhenium ion, but at least it's not a very unstable rhenium ion like the ortho and para attack would form. So we say then the nitro group is a meta director because even though it has a high activation energy, it's not as high as would happen from ortho and para attack. Okay, so again, let's summarize, right? All of the activating groups are ortho-para directors, and almost all of the deactivating groups are meta directors. Halogens are an exception. So we'll actually say the moderate and strong deactivating groups are meta directors, but the halogens are a little bit weird. Halogens are technically deactivators because, for example, chlorobenzene reacts more slowly than benzene in an electrophilic aromatic substitution reaction. So technically we call it a deactivator because of the rate difference. However, it's still an ortho-para director, which is a little bit strange. The reason for that is because of the special properties of the halogen. We know it is electronegative and it's pulling electron density out of the ring through induction. You can also think of the lone pair on the chlorine as possibly donating some electron density into the ring, like similar to how an oxygen or a nitrogen atom with a lone pair would donate electron density into the ring. The problem is chlorine will use its 3p orbital to overlap with carbon's 2p orbital. That ineffective orbital overlap leads to these 3 resonance contributors being very insignificant contributors. So while they donate electron density into the ring via resonance, not very well or not very strongly compared to like a methoxy group, for example, because of the mismatched p orbital size between chlorine and carbon. So it's kind of a little bit strange. Overall, the inductive effect leads to it being deactivated. However, the resonance donation, albeit weak, still leads to it being a orthopara director. So all of the activators, including the halogens, which are technically deactivators, are orthopara directors, and the moderate and strong deactivators are meta-directors. Here's the rhenium ion. Even though this is not a very significant resonance contributor, it donates enough to the stability of the rhenium ion that it's more stable than the meta attack, and as a result, it ends up being an orthopara director, the halogens do. So here are some examples of strong activators and moderate activators. If you look at the structure, think about what's the difference between the structure. All of them have an atom like oxygen or nitrogen with a lone pair on the benzylic position, right? But the moderate activators also, for the most part, have a carbonyl group, okay, outside of that as well. So the way I think about it is the lone pair is partially tied up in resonance outside the ring. So partly the electron density from the lone pair is on this oxygen. So if it's on this oxygen, it's not being donated into the ring as effectively as if there wasn't a carbonyl to donate electrons to. So all of these are strong activators, and with a carbonyl, they become moderate activators. So they still donate electron density into the ring, but again, some of that electron density is up here on this oxygen, so it doesn't donate as effectively. The methoxy or ethoxy group is actually in the moderate category compared to like a hydroxy group of phenol. And I don't get into this extremely strongly, but we'll talk about it a little bit in the lab. Specifically, it has to do with the electron density of the lone pair in the p orbital on oxygen being tied up through hyperconjugation or no bond resonance with the methyl group, if this is a methyl group here. So that can be the reason why it's not quite as electron donating into the ring, and it ends up more in this moderate activating category than strong activating. But of course, this is determined based on rate, right? Rate of these substrates compared to benzene. So of course, somewhere there's going to be a line drawn in the sand. Everything on this side is considered moderate, everything on this side is considered strong, but where does somebody draw a line in rates? So that can vary depending on the person drawing the line, which can then affect sort of where these compounds go in terms of their category. So the weak electron donating groups, also orthopara directing, are the alkyl groups. Remember, those don't donate through resonance, so they don't donate as strongly into the ring. They do donate through hyperconjugation, so they are electron donating, just not quite as strongly. Okay, let's talk about the deactivating groups. We talked about the fact that the nitro group is a strong deactivating group, but there are others as well. Look at this carbon with 3 halogens, like CCl3 or CBr3. Those have cumulatively, because there's 3 electron withdrawing groups attached to this carbon, cumulatively they have a very powerful inductive withdrawing effect, and they end up in the strong deactivating category / electron withdrawing category. Also, a nitrogen with a positive charge is powerfully withdrawing electron density out of the aromatic ring to try to satisfy this positively charged nitrogen. The moderate activators all have something in common. They have a carbonyl directly attached to the aromatic ring, right? There's no oxygen in between here, it's directly attached. So those are all of the functional groups like ketone, aldehyde, ester, carboxylic acid, amide, or even sulfonyl. Think of this as kind of like a carbonyl, or even a nitrile, which has a carbon-nitrogen pi bond as opposed to a carbon-oxygen pi bond. Remember, the halogens are the ones that are weird. Technically, they're deactivating, but still orthopara directing. And so, you know, they're kind of in their own little world. Let's do some practice problems. Okay, we are going to predict the major product for each of the following reactions. The goal here is to look at the group on the benzene ring. Think about if it's going to be an ortho-para-director or a meta-director. Remember, ortho-para-directors always direct para first. And think about the incoming electrophile, right? And put it onto the ring in the correct placement, right? To either put it in the ortho, meta, or para position. Go ahead and stop, and we can go over it when you're ready. Okay, let's go over the answers here. So the hydroxy group is a powerful activator, right? And an ortho-para director as a result. And it's going to direct para first, right, over ortho because the para position is available. So that means we are going to introduce our new electrophile and put it in the para position. Right, so we're going to add an ethyl group at the para position because we're doing a Friedel-Crafts reaction with ethyl chloride, alkylation reaction. Okay, what about toluene? Toluene, again, that methyl group is now a weak activating group, but it is still an ortho-para director. So the incoming acyl group for this Friedel-Crafts acylation reaction will still go para, because the para position is not blocked, right? So para first. So we'll introduce this acyl group and put it in the para position. Nitrobenzene, remember that nitrobenzene is the nitro group is a strong deactivator, and so that makes it a meta director, right? Remember that we cannot do any Friedel-Crafts reactions, but this is not a Friedel-Crafts reaction. This is a chlorination. We can do that, and we're going to place that chlorine into the meta position because it's being directed there by the nitro group. This is a moderate deactivating group because the carbonyl is directly attached to the ring. So it is also a meta director, right? Again, we would not be able to do a Friedel-Crafts reaction, but we can introduce a nitro group onto this ring. So we are going to make sure to introduce that nitro group into that meta position. All right, back to the slides. So let's look at when there's multiple directing groups attached to a ring. Where do we put the incoming electrophile? Well, we have to take into account all of the substituents attached to the ring and think about where they are directing. The methyl group is an ortho-para director. The para position is blocked by the nitro group, so it is directing to its ortho positions here. Right? Ortho to the methyl are these positions. Nitro group is a meta director, so it's directing meta to the nitro group, which actually is the same positions. And because there's an internal plane of symmetry, it doesn't matter if we put the bromine here or here, it's the same product, right? So just put that bromine into that position, and that's where the bromine is directed to go by both of the substituents. What about, so remember we talked about with ortho-para directors, the major product is placing that incoming electrophile at the para position because of sterics, preventing it from going into the ortho position. Let's think about two different groups, alkyl groups. Now we have a methyl group and an isopropyl group. Both of those are ortho-para directors. The para position is blocked, right? So the para position of this isopropyl group is this position, and it's blocked by the methyl. And the para position of the methyl is blocked by the isopropyl. So the ethyl group is directing here. The methyl group is directing ortho to it. So really all of the positions are being directed to. If we think about the category, the methyl and the isopropyl are in the same category. They're both weak activating groups. So there's no preference based on which one is the stronger activating group. So in this case, it's just going to be steric hindrance giving us the major product. It's steric. Sterically, it's not as bad to put a nitro group next to the methyl compared to next to the isopropyl. Again, this is another steric situation. If we think about what's being directed, right? These groups are ortho-para directors. The methyl is directing here, here, and here. The isopropyl is directing to all the same positions. These are the two ortho positions to the isopropyl, the para position to the isopropyl. So all three of these positions are being directed to equally, but what's the best in terms of steric hindrance? It's best to put the nitro group next to the methyl. And it's really bad to put it in between the two groups. That would be the most sterically hindered situation. All right, so let's do some more practice problems. I would like you to consider both directing groups if there's more than one directing group, and think about where the incoming electrophile will go. And remember that if you have one group that is let's say, for example, a strong ortho-para director, a strong activator and ortho-para director, that is more important than a weak ortho-para director. So we always listen to the strongest activating group first if there's any discrepancy between the two. And if not, maybe steric hindrance will be the dominant factor. So go ahead and try to predict where all these incoming electrophiles would go and draw the major product of this reaction. And we'll go over the answers shortly. So I am actually going to stop here because my babysitter is scheduled to leave at 5 o'clock, and it's 5 o'clock right now. And I will make another video from this point forward.